Hello and welcome. In this video, we're going to be looking at neural networks for classification tasks. In the previous video, we saw how neural networks can reproduce nonlinear input-output relationships and can be used for regression. And we can fit arbitrarily complex functions by adjusting the weights and the biases during a training phase. The architecture of a neural network for classification is pretty much the same. Uh, and in the case of the simplest neural network, you're going to have one input node, then one hidden node, and one output node. And of course, you have the corresponding connection weights and connection biases. The and this is the simplest neural network, but we can have even more complex neural networks. For instance, we might have a neural network um, which might have three input nodes, and these three input nodes can be connected to a hidden layer with multiple hidden neurons, maybe 4 or 5 hidden neurons. And while this video is playing, you will notice that each input node is connected to every neuron in the hidden layer. So with 3 input nodes and 4 neurons in the hidden layers, we have 12 connections between the inputs and the first hidden layer. Then we have a second hidden layer. And in the second hidden layer, we have multiple neurons again. And you can see that the network is fully connected, which means that every neuron is connected to every other neuron in hidden layer 2. And they have the corresponding weights and the biases. This leads us to hidden layer 3, where we have 3 hidden neurons. And finally, we have the output node, where we have the corresponding connection weights and connection biases. And in regression mode, you can see how the input values progress uh, through the activation layers and the weights and the biases, and finally give us an output, a number, a continuous output value. And we can essentially use a network like this for regression. A thing to keep in mind is that we can have networks of arbitrary complexity. We can have multiple inputs and multiple output nodes. So this is for regression. How do we adapt something like this for classification tasks? Let's take the very simple case of binary classification. And since the network is pretty much the same, we're going to have input features. We're going to have the weights, which are connecting the input to the hidden layer. We will have the biases. We'll have an activation that operates on the inputs. And finally, we go to the output layer, where we have another set of weights and another bias. The difference for classification tasks is that we pass the output through something called a sigmoid activation function. And this sigmoid activation function allows us to convert what are real numbers on the real axis, which can be -infinity to +infinity, into probability values. Probabilities, as you all know, will take values between 0 and 1. And so we can convert the output into probabilities by using the sigmoid function, and essentially saying that we're going to label the data as one specific class if the probability exceeds 0.5, and we're going to label it as the other class if the output probability is less than 0. Let's see this in action. So we're going to be doing binary classification. Binary classification involves labeling a input data point into one of two different classes. So we have an input, we have these two hidden neurons, and we have a probability on the output side. So the question is, how do we go from something that looks like this to something that looks like this on the output side? So the panel on the left represents what might be a typical uh, output from a neural network. But what we want on the output side is something that looks like this, which represents probabilities. So just to give you an example, we might want to classify different intervals as shale or clean formations based on their gamma ray values. So if the gamma ray value is less than 100, we call it a clean formation. And if the gamma ray value is larger than 100, then we call it shale. And so we would ideally like to have a output probability that looks something like this, where if the input gamma ray value is less than 100, we're going to output probability 0, uh, which refers to the probability that it's not a shale and it's a clean formation. And if the gamma ray values are larger than or 100, then we output the probability of 1, and the point is going to be labeled as a shale. So this can be done using something like a sigmoid function. If I pass this output through a sigmoid function, I'm essentially going to be getting probabilities on the output side. So let's see how that happens. Well, the sigmoid function looks like this. And you can see that we have real numbers on the x-axis going from minus infinity to plus infinity. And on the output side, the values are restricted to 0 at a minimum and 1 at a maximum. So that's your sigmoid function. And essentially, if you pass the output of your neural network through a sigmoid function, it essentially adapts the neural network to be able to do classification tasks. And you end up with a plot that looks like this on the output side for different input values. In this specific example, you can see that if the input gamma ray value is less than 100, we're going to label it as class 2. And if the input value is larger than 100, we're going to label it as class 1 based on the probabilities that we determine. Okay, so that's a neural network for binary classification. Let's take a closer look at the sigmoid function. This is the equation of a sigmoid function. It has a parameter beta and the input variable x. And beta essentially controls the sharpness of the curve. We aren't going to be playing with beta right now. What we're going to be doing is just looking at the basic sigmoid function where beta is equal to 1. So I've coded this out. This is my sigmoid function, and I'm going to generate 100 values of x between a negative 100 and plus 100, and we'll plot the corresponding sigmoid function. And if you do this, then we end up with an S-shaped curve like this. And with the S-shaped curve, you can see that for values of x between negative 100 and 0, the output probability is less than 0.5. And for values between 0 and 100, the output probabilities are uh, larger than 0.5. And so we can use the sigmoid function for binary classification. The function would look a little bit more smoother if I choose more points, for instance, maybe 500 points. Uh, you can see that now the function looks significantly smoother. All right, so let's go ahead and apply uh, our own or construct our own neural network and apply it for classification tasks. Specifically in this example, we're going to classify data point as class 1 if some attribute or some feature associated with it has a value larger than 20. And if that value is less than 20, then we're going to label that point as class 0. So I have my sigmoid function over here, and then I have a one layer single neuron, one hidden layer with one single neuron uh, network with one input node and one output node. So I have the weights and biases coming from the input node to the hidden layer, and then the weights going uh, to the connection between the hidden node and the output. So scalar values, because we're just dealing with one node, one hidden layer, and one output. And we're going to pass uh, the output through the sigmoid function, and we essentially get some probabilities, and we're going to return a value of 1 if the output is larger than 0.5, else we're going to be returning a value of 0. So if you did something like this, then we want to see what values or what this neural network is going to label a bunch of inputs. We're just going to arbitrarily choose some input values, -7, 49, 64, 23, 99, and 12. And let's see what it labels these points as. So you can see that x equal to -7 was labeled as class 0, x equal to 23 was labeled as class 1, and x equal to 12 was labeled as class 0. And we can play with these input values. We can try different input values. We can try -100, we can try 2, then we can try 23, and we can try 45 and see what we get. And in this case, the outputs are going to correspond to what the neural network has been designed to do. And this is good. This is a very simple neural network with one hidden neuron and one input node and one output node. So let's go ahead and apply a neural network for classification on a more realistic data set. The specific data set that we will be dealing with is a very, very well-known data set for machine learning applications. It's called the IRIS data set. It has a bunch of measurements on several flowers, and these flowers are all irises, but there are subspecies of irises, and there are three subspecies. So we have a data set that contains measurements on the flowers and the label, the subspecies label associated with each one of those inputs. And we'll take a look at the data set in a minute. So I'm going to read in this data set, and I'm also going to be assigning uh, I'm going to be creating a data frame which contains my input features and another data frame which contains my target variable. And I'm going to plot the data set using a Seaborn pair plot. So this is what the data looks like. There are 4 measurements. I have sepal length, sepal width, petal length, and petal width. And there are 150 data points. And these points are labeled according to the subspecies they belong to. So the green points refer to Virginica, the orange points refer to versicolor, and the blue points refer to setosa. So what we want to do is we want to construct a neural network classifier that digests this information so that it can make a prediction on new data points. If I fed that neural network um, data related to or inputs related to sepal length, sepal width, petal length, and petal width, it would be able to tell me what the subspecies label is. All right, so let's proceed further down. So in this case, you will notice that we're not doing binary classification. What we're doing is multi-class classification problem. We have 3 classes, and for most classification problems, it doesn't have to be a binary classification um, problem. It can be, we can try labeling 16 classes or 10 classes, and in this case, 3 classes. So how does this happen? Well, the neural network architecture is pretty much the same. We are going to have some input nodes, and in this case, we have four input nodes corresponding to each of the four measurements. That's sepal length, sepal width, petal length, and petal width. And we can choose as many hidden layers as we want and as many neurons as we want for each one of the hidden layers. So, and of course, it's a fully connected network. So we can see that each of the input nodes is connected to each of the hidden neurons. So I have hidden layer one, and I also have hidden layer two. Hidden layer one, you can see has 5 neurons, and hidden layer two, we'll soon see, also has 5 neurons. And this is just an arbitrarily chosen configuration. In general, you can choose a neural network with any number of hidden layers and any number of neurons. And you would choose a neural network of appropriate complexity by doing some validation tasks. Typically, what we do is 5-fold cross validation or 10-fold cross validation. And then I have hidden layer three, which has 4 neurons as well. And something to keep in mind is that this is a fully connected network, and in each of these hidden layers, we have the ReLU activation function. And finally, we have output nodes. In this case, we have multiple output nodes because we are going to be outputting probabilities associated with each one of the classes. So the first node is going to be outputting the probabilities associated with class one. The second output node is going to be providing probabilities associated with class two. And the third one is going to be providing probabilities associated with class three. And so for a given set of inputs, you can see that we get the outputs, output probabilities, and the output probability should add up to 1. And in this case, the maximum probability is associated with label 2. And so we might label this specific data point as setosa or versicolor, depending on what label 2 refers to. And with some other set of inputs, we might get a slightly higher probability on the first output node or higher probability on the second, third output node. Whichever has the highest probability is what the neural network is predicting that specific data point to be. So this is how we do multi-label classification using a neural network. So continuing with our tasks, we first split our data set into a training set and a test set. I'm going to be using a test size of 20%, which means that my training data set has 80% of the 150 points chosen randomly. Something that I'm not doing over here is what's known as a stratified split, which we will discuss later on. I'm also not doing any kind of cross-validation yet. We're simply doing a train and test split because right now we're focusing on the neural network and the functioning of a neural network. So we're going to take my input features X and my target variable Y, and we're going to split them into 4 arrays. And we're going to scale my input features, both in the training set and the test set. And we're also going to be defining a neural network classifier using the sklearn library. And the specific command for that is MLP classifier. And just arbitrarily, let's just choose a very simple network with 3 neurons in the first layer and 3 neurons in the second layer. I have an activation function. That's the ReLU activation function in each one of these hidden nodes. And then I assign a random state to some integer value. And the reason why I do this is because every time I run this code, I want to get exactly the same answer. So I want the neural network to initialize from the same initial values of weights and biases so that I end up with the same answer each and every time. Then I train my model, which means that I fit this model to my training data set. And the model is going to try to replicate the label data. The data is going to be fed in one by one, and predictions are going to be made about the predictions of the label associated with that data point are going to be made. If there's a discrepancy in the prediction, then we're going to adjust the weights and the biases. And all of that is encompassed in this uh, fit keyword that we are using over here. So we're going to train our neural network, and hopefully it's trained by now. So once the neural network has been trained, we need to test the neural network. So what we do is we take this model, which I'm calling the MLP model, which refers to the MLP classifier with 3 neurons in the first hidden layer and 3 neurons in the second hidden layer. And I'm going to make predictions on my test data set. And finally, I'm going to output the accuracy of these predictions. So you can see that we get an accuracy of 70%, which isn't all that great, but isn't all that bad either. And the accuracy essentially refers to the number of correct predictions it made based on divided by the total number of predictions. So, and that's a good number to keep in mind, but it's not the only metric that we're going to be looking at when we're dealing with classification tasks. I want to discuss why that might be the case. Now, if you consider designing a flu test, for example, you might uh, want to collect a sample population of, say, 10,000 people, and you might go and swab uh, everybody and collect those swabs. And essentially, what you could do with those swabs is you could just throw them away. And you can simply say that nobody has the flu. And you would be about 98 or 90%, 99% accurate, because on any given day with any given sample population, it's unlikely that more than 1 or 2% of the population has the flu. And so if you do absolutely nothing and just say that nobody has the flu, you're about 98 or 99% correct. And this happens when you have infrequent classes. The occurrence of flu in a population is very rare. So your accuracy is artificially high. Another case where this might occur is when you're trying to predict equipment failure from using real-time data. So you might construct a classifier that takes in real-time multivariate data streams and is trained to recognize normal operation and failure modes. You could, of course, spend quite a bit of time and effort to construct such a classifier. Or alternatively, you could just say that there are no failures at all, irrespective of what the input features are or the input feature values are. And you would be right 98 or 99% of the time, because failures are essentially rare occurrences. And so, for the most part, your equipment is going to be operating normally, and uh, you would not have more than 1 or 2% of the time would you have failures. So you can see that accuracy is a good metric, but it's not all that you should be looking at. What we need to be looking at is something called precision and recall, and something called the confusion matrix. The precision and recall provide a little bit more information. The precision is telling you how many true positives you have divided by the number of true positives and false positives. And the recall is the same thing in the numerator, and the number of true positives on in the denominator added to the number of false negatives. So this is where you can see that if you make false predictions, either false negatives, uh, when you say that nobody has the flu when 1 or 2 people do have the flu, or when you have false positives, your rate, your precision, and or your recall are going to go down. And so if your precision or recall goes down based on what you're doing, that's an indication of a classifier that's acceptable, or perhaps a classifier that needs further tuning. And so in general, what people look at is something called the F1 score, because the F1 score is nothing but a harmonic average of both precision and recall. We want a low false positive rate. We also want a low false negative rate. And so if you look at the F1 score, we're essentially quantifying uh, what's the false positive rate and what's the false negative rate. And we want them both to be low, or in other words, we want both the precision and the recall to be high. And so F1 scored the harmonic average of precision and recall will penalize any value that is low. If precision is high and recall is low, F1 is going to be low. If precision is low and recall is high, F1 will be low. And that's just the nature of harmonic averages. So we can also look at the F1 score. Um, and a very important thing to look at when you're doing classification is something called the confusion matrix. And the confusion matrix in this specific example looks something like this. So to explain this, you can see that these are the true labels from this test data set, and these are the predicted labels. And each of the entries over here correspond to what the classifier is telling you on the test data set. So when the true label was setosa, our classifier predicted label was setosa 10 times, and it did not make any misclassification errors and label them as versicolor. Neither did it label any of the setosas as virginica. So as far as setosa is concerned, the classifier is doing very well. On the other hand, when the true label was versicolor, it misclassified 3 points as setosa and essentially didn't label any of the points as versicolor and labeled 6 of the points as virginica. And it got the versicolor entirely wrong. On the other hand, if the true label is virginica, it got all of them correctly classified. And this is a classifier that's perhaps uh, not a great classifier and can definitely be improved upon. But the point about the confusion matrix is that you're looking for a very strong diagonally dominant confusion matrix, and you want the off diagonal terms to be as low as possible because the off diagonal terms represent misclassification errors. All right, so we can try a slightly different neural network with maybe slightly more complexity. We could perhaps try uh, 20 neurons in the first layer, 10 neurons in the second layer, and 10 neurons in the third layer, and see how well this one performs after fitting it to our training data set. So we finish fitting it to our training data set. We're going to make predictions on our test features, and we get close to about 97% accuracy, which is fabulous. Uh, and if you look at the confusion matrix looks like this, where there's only one point which was misclassified and it got all of the other points correctly labeled. So to end this discussion, uh, neural networks are well suited for classification tasks. And essentially what you would need to enable classification is the sigmoid function, which takes any real number from -infinity to infinity and transforms it into values between 0 and 1. And so we can use the values between 0 and 1 to represent the probability of a specific label or a specific category. In this specific notebook, I used a simple train test split. I didn't do something called a stratified split, and that will come later. And in terms of gauging your model performance, we typically look at the confusion matrix. We look at the F1 scores, precision, recall, and accuracy. But accuracy should not be the primary metric by which we assess model performance. So with that, uh, we looked at neural networks for classification, and that brings me to the end of this video.